Okay, this is video number 2. We've got a more detailed example of the method of joints for finding internal forces in members of a structure. So our objective then is to find forces inside members, and if you remember, there are two big ideas. If a structure isn't moving, we don't want it to be moving. All external forces are in equilibrium, and all forces at all joints are also in equilibrium. So let's get started. The procedure that we'll follow is the same as before. We'll draw a free body diagram, check for determinacy to see if we can solve the problem, calculate reaction forces, and then get into calculating internal forces. Okay, so the problem is this. We've got a more detailed truss here with two loads on it. And notice on the left-hand reaction, we've got this indicates a pin connection, which means the reaction forces are not necessarily vertical, right? So we'll get into that in a minute. So let's draw the free body diagram, which looks like this. So the free body diagram has all of the external forces shown in blue. The dimensions are shown, and each point is labeled. Okay? Notice there's a potential horizontal component to this reaction force here. On the right hand side, this is a roller, so there's no horizontal constriction, as similar to the nutcracker example from the last video. Okay. So let's first check for determinacy. How many unknowns do we have? We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 members, and we have 3 reaction forces that are unknown. So that is 16 unknowns. We have 8 joints at which we can generate 2 equations, right? Summation of vertical forces and summation of horizontal forces. So we've got 2 equations times 8 joints. That's 16 equations, 16 unknowns. We can solve this. This is statically determinate. Okay, so the next step is the calculation for reactions. The summation of horizontal forces is 0. We know this. There's only one horizontal force, which means it must be equal to 0. Summation of vertical forces is equal to 0. We've got a minus 6, a downward 6 kilonewton force. Another one, and then we've got 2 vertical reaction forces, one at A and one at E. Okay. We don't know how much each is, but we know they add up to 12. So we need to take moments about a point to get to find the actual values. We'll take the moments about point A because one of the forces goes through A, and therefore there's no moment caused by that force. It gets rid of the unknown. So summation of moments about point A is equal to the reaction force at E times the distance away, which is 12 meters, and it's a counterclockwise moment, so therefore it's positive. We have a 6 kilonewton force times 3 meters away. It's clockwise, so it's negative. Similarly, 6 kilonewtons times 6 meters away, clockwise, so it's negative as well. So if we solve for the reaction force at E, it comes out to 4.5 kilonewtons. Now we can go back and plug that value back into this equation, bring it down here, and we've only got now one unknown, the reaction at A, and that's equal to 7.5 kilonewtons. So here we are. So now we can start isolating joints and calculating forces. So I didn't mention this before. The way that we choose which point to isolate next is by virtue of how many unknowns are connected to it. So For example, if we choose point A right now, how many unknowns are there? Well, there's an unknown force in AF and an unknown force in AB, but that's it. Only two unknowns. And we can always have two equations, right? Summation of vertical forces, summation of horizontal forces. So therefore, two equations, two unknowns. This is a good point to isolate. Okay? So we'll isolate point A here and find the forces at A. So the forces at A, now again, there's something else I didn't mention the last time. It's a good idea to always assume the unknown forces are in tension. So they're pulling away, and I'll show you why in a minute. Okay, so this is the free body diagram of joint A. We have two unknowns and one known force. If we break this force AF into its components, looks like this. Okay. Now we need to calculate those. So AF is the hypotenuse. Notice this is each of these is a 3, 4, 5 triangle. So the sines and cosines are pretty straightforward. So the vertical force, vertical component of AF is equal to the sine of that angle, that base angle, times the hypotenuse. So it's 4/5. The 3, 4, 5 triangle, the sine of the angle is 4/5 times the hypotenuse. The horizontal component is the cosine of the angle, which is 3/5, 3/5 times the hypotenuse. And so now we can do the summation of vertical forces is equal to 0, a plus 7.5. And then we had assumed this was in tension, so it's pulling away, so it's up, plus F sub AF. Well, when we solve for that, it comes out negative. So we know, since we assumed it was tension and it came out negative, we know our assumption was wrong. So therefore, it's in compression. Okay, so if we always assume tension, if the answer comes out negative, we know it's in compression. So the hypotenuse is equal to the vertical leg divided by the sine of the angle. So it's equal to 9.375 kilonewtons compression. Summation of horizontal forces, we have F sub AB, we have AF, but now we know, remember we know now this is in compression, so this arrow should be going in the other direction. So it's a negative, and AB then is 9.375 times the cosine of the angle. Right? Right. So FAB is 5.625, and we know it's in tension because it came out positive, and we had assumed tension. Okay, so now we have these two internal forces. So now which point should we isolate? Well, if we go to F, there are 3 unknown members attached, so that's not a good choice. So let's go to point B. There's only 2 unknown members attached. So let's isolate point B. It's easy. Everything is XY, so we don't have to make any conversions. We'll assume the unknown BF is tension, BC is tension, we'll assume. Summation of vertical forces, minus 6 down, plus F sub BF comes out to plus 6, so, and it's positive, so that means our assumption of tension was correct. So 6 kilonewtons in tension, and summation of forces horizontal, F sub BC minus this comes out positive, so we know that the assumption was correct. So 5.625 in tension. Okay, so now we're moving along here. Let's go to point F, because there are now only 2 unknowns. So now this is a little more complicated. Now we have a couple of forces acting here that are not horizontal or vertical. So we need to convert them to their horizontal components and vertical components. We're assuming that this is the unknown. We're assuming it's in tension, remember. We don't know, but we're assuming. This one we know is in compression, so it's toward F. And we know its components already. So the summation of verticals is equal to 0, and we know there's a plus 7.5, a minus 6, and a minus F sub FC vertical. And if we solve for that one unknown, it comes out to 1.5. It's positive, therefore our assumption that it was in tension was correct. Okay. So now we can solve for the hypotenuse. Again, the hypotenuse is equal to the vertical divided by the sine of the angle. So it's 1.875 in tension. If we do the horizontals, there's 5.625 plus the horizontal component of FC plus FG. Okay, we assumed FG is in tension. So 5.625, the horizontal component of FC is FC, 1.875, times the cosine plus FG. And solve for FG. Well, it comes out negative. We assumed tension, but it comes out negative, so we know our assumption was wrong. So it's 6.75 in compression. Okay, so now we're moving right along here. Let's isolate point G. It's only got two unknowns. And there are all vertical horizontal forces. We're assuming that the unknowns are in tension. Summation of verticals. There's only one force vertical, and it's got to equal 0. So GC is 0. Summation of horizontals, we have 6.75 plus GH. Well, if we solve for GH, it comes out negative. Therefore, we know that was a bad assumption. So we know that it's in compression. The arrow should go in the other direction. 6.75 compression. Okay. So now let's isolate point C, because there's only two unknowns. So here we are again, a little more complicated. We're assuming tension again. These are the two unknowns. Break them into our components. Here we have these components. Summation of verticals, 1.5 plus CH vertical. Well, when we solve for that, it comes out negative, so we know that that assumption was wrong. It should be compression, so this should be in the other direction. So the hypotenuse, again, vertical divided by sine, 1.875 in compression. So the summation of horizontals is minus 1.125 minus 5.625 plus the assumed tension F sub CD, but now we know CH is in compression, so we know it's in the other direction, so it's minus. We already know that. And now we're going to plug in the value for the horizontal component of CH, which is CH times the cosine. Solve for CD, comes out positive, so we know the assumption of tension was correct, 8.625. There we are. So now we're going to do, I think, in the interest of time, we're just going to talk through these last couple. First of all, if we look at point D, there are no vertical forces other than this member here, HD, so that means it's got to be 0. If we look at joint D again, this force here has to compensate this force, therefore it's got to be 8.625 in tension to balance this one out. And then finally,